We're in 20.1. We're doing scale factor today. The scale factors are really handy because it allows us to shortcut a lot of the calculations that we would do when we um, multiply something by a scale factor. So we're going to look at the effects of that here. So we're going to start off by talking about perimeter and area. That's the first question they ask. Find the perimeter and area. But first we want to find the perimeter and area of the pre-image here. So we should be pretty familiar with how to do this. One note, each unit here on the graph is actually 1/2, right? So this is 1, this is 2, this is 3. So the distance between B and C here is 1, 2, 3. So that's 3. The distance between A and D is 1, 2, 3, so that one's 3. So if I were to write down the perimeter, I would say that the perimeter is equal to, that's the sum of all the sides, right? So that's 3, so it's going to be 6 plus something else. In this case, I can draw this, I could use a distance formula and find the distance between A and B, and you could figure it out that way for sure, right? But note here, we could also, the way I prefer to do it is to use the Pythagorean theorem. So there's no subtraction involved, just counting the distance. But note here, what type of triangle is this? Well, as it turns out, it's an isosceles right triangle. So therefore, it's a 45, 45, 90 triangle. And if this side, we'll get rid of that 3. If one of the sides is, say, x, we should know what this other side is. It's one of the, this is one of our special right triangles. So I'm going to put this side in as 2, right? Because this one's 2. And if you can't remember the special right triangle here, that's okay. The downside is if you want this in simplest radical form, you're going to need to work through that yourself. But if you were to use Pythagorean theorem, you'd find it's the square root of 8. If you remember the pattern here, whatever this side x is, the hypotenuse is going to be x times the square root of 2. Square root of 2, in this case x is 2. So this side length is 2 times the square root of 2. This side length, incidentally, is also 2 square root 2. So for the total perimeter, we can say it is 6 plus 2 square root 2 plus 2 square root 2, or plus 4 square root 2, right? Because we have 2 of these things, or two pairs of these things. So our total perimeter is this. Area. Some of you don't remember area for parallelograms, but another way to think of this is if we broke off this chunk here and then simply, picked it up, moved it over, ta-da, and make a rectangle. It's the same base as this base and the same height. The area formula for a rectangle is base times height. So in this case, the height is 2, the base is 3. So we can say that the area is 2 times 3, or 6 units. Right? That should be pretty straightforward. I'll go ahead and apply this transformation here too. While we're doing, we'll do a red one, I guess. It's going to look weird because the book kind of forgot to make this the right size, or make a graph the right size. So we're simply going to multiply each x value by 3. So this one is 0, so it's b prime stays here. D has a value of 1, so it ends up over here. This one's trickier. It has a value of -2, so it ends up like here-ish. And then this one's super ugly. We gotta get them all the way out here-ish. Something like that. So, nice straight lines. Oh golly, that's not straight at all. That's embarrassingly not straight. Okay, I'll fix it. Then this one's a little straighter. Okay, so we have this beautiful parallelogram that I've just drawn, and it's done this transformation, right? So the question is, what is the new perimeter? What is the new area? And we'll do area first. It's a little easier. So again, the area is the length of the base times the height. Well, the height didn't change, it's still 2. The length of the base, in this case, it was 3, and now it's 9, right? We could count out the units. Again, if it was graphed accurately, it would be a little easier. But it was previously 3, and we know it's 3 times larger. So that means the length of the base is 9. What is 9 times 2? It's 18. Some of you guys may have been able to figure that out without doing the 2 times 9 thing. And we'll come back to that in the patterns that we see emerging here. The perimeter is going to be a little trickier. The top and the bottom, the 2 bases here are both 9, so that's going to be 18 plus something. If we again use our kind of Pythagorean theorem here, I'm going to think of my triangle. All the way over here, all the way up there. This one has a height of 2. This one used to have a width of 2. Now it's going to have a width of 6, right? So we'll call this C. A squared plus B squared equals C squared. So the square root of 36 plus 4, right? This is 6 squared, this is 2 squared. So the square root of 40. And we can split square root of 40 up into the square root of 4 times the square root of 10. And then we all know what the square root of 4 is. That's 2 square root 10. But wait, there's 2 of those. There's one here, and there's this one here. So instead of being 2 square root 10, we might as well put in 4 square root 10. 4 square root 10. Okay, so those are the values we can plug in for the perimeter and area of the original, and the perimeter and area of the base. And that's these ones here. So we have the perimeter of the original, the area of the original, the perimeter of the new transform figure, and the area of the transform figure. So some of you may have noticed there's a bit of a pattern here. The area went from 6 to 18, right, when we multiplied all the x's by 3. So to do this, we multiply it by 3 to go from here to here. It doesn't work for perimeter, though. Notice that if we try to multiply both these terms by 3, that would give us 18 plus 12 times the square root of 2. 12 square root of 2 is not the same as 4 times the square root of 10. So there's nothing really that we can conclude here. We're going to try it again this time. Instead of going horizontally, stretching it, we're going to do a vertical stretch. So you can see here that our y values are being multiplied by 3. I'll go ahead and graph these ones. I'll make this one green, I guess. 1, 2, 3 times higher. So there's B prime. Here's C prime. It's going to be off a little bit. 1, 2, 3, 4. Right there. And this one will be right. Nope. Extend a little bit. Okay. Nice, perfectly straight lines. Doody-doody-doody-doody-doo. Doody-doody-doody. Yep. Don't wiggle. Oh, golly. Okay, cool. Same sort of deal here. Perimeter is equal to the bases, so that's 1, 2, 3, plus 1, 2, 3, so that's 6, plus the length here. Again, I can kind of form a right triangle. Think of this right triangle, this blue right triangle. It has a width of 2, it has a height this time of 6. Therefore, the length of that, we've done this one, right? It's 36 plus 4, or 40. So the square root of 40, or 2 square root 10 is our length here. 2 square root 10 there. So our final length is 4 square root 10. Cool. Erase these temporarily. go there. Didn't need to do that. View more. View more. 100%. Yeah, that's pretty good. Okay. Now we need to do area. Again, area is usually pretty easy relative to perimeter. The area is the base times the height. The base is 1, 2, 3. The height is 1, 2, 3, 4, 5, 6. 3 times 6. We can do it in our head. 18. Okay, so that gives us these. After this transformation, the area is again 3 times larger, right? We multiplied this area by 3, which was our scale factor. But again, there's no pattern. It's a different perimeter, and there's no pattern, right? So there's a different change for the perimeter based on whether we do a vertical stretch or a horizontal stretch, and it's not predictable either way. So just keep that in mind. There is no pattern here, even though there is a pattern. When we just stretch it horizontally or just stretch it vertically, the scale factor, in this case 3, is what you multiply the area by. So we multiply the area by 3, and that gives us 18. It doesn't matter if it's vertical or horizontal. Again, the reason why we're multiplying by 3 is because that's our scale factor. Okay, let's try a few more. This one, we're going to multiply both the x and the y by 3, right? So instead of doing just a stretch horizontal or a vertical stretch, we're going to do a proportional dilation. We've done dilations before. Remember, they preserve similarity. So I'm going to go ahead and do that dilation to each one of these points. I'll start with the easy ones. B prime and D prime. C prime is going to end up way over here somewhere. I'm just ballparking. This guy's going to end up way over here somewhere, and then I draw some super sweet straight lines. Ooh, that wasn't bad. Done much worse in the past. There we go. Cool. Done. Not bad. Okay. Perimeter and area. Start with the perimeter. Perimeter is equal to, again, we'll start with the bases. They were 3, now they're 9, right? This length here is 9. This length here is 9. So I'm going to put an 18 plus, I should probably do that in a different color. Again, I have a right triangle. Where's that one? I'll do it in red, I guess. I have this right triangle that I'm trying to find the hypotenuse for. It's a right triangle with equal side lengths. This is 6. This is 6. So therefore, this side length here is going to be 6 times the square root 2. And I know that because it's a special right triangle. If you want to do the Pythagorean theorem, feel free. This side here is also 6 square root 2, so our total perimeter is 18 plus 12 square root 2. Cool. So that's perimeter. Next up is area. The area, again, relatively simple. The height, which is 6, times the base, which is 9. Area, therefore, is equal to 54. This is by far one of the things people mess up on most. They think that they should be, the area is much smaller than it really is. So let's look at the pattern. We started with 6 plus 4 square root 2 for the original perimeter. After a dilation of 3 in both directions, we have 18 plus 12 square root 2. So a lot of you guys can figure that out, that this is actually just multiplying by 3, right? Distributing to both terms. So 6 times 3 is 18, 4 times 3 is 12. Therefore, this value is 3 times this original perimeter. And then finally, the area here is a little more interesting. It used to be 6, but now it's 54. Well, is it turns out we're multiplying by 9 this time. And the reason why it's 9 is because it's 3 squared. The one of the reasons why I like to explain this is because we're in a different dimension now. Perimeter is a single dimension, right? It's just length. Each individual, yeah, it's a 2D shape, but the perimeter is the sum of one-dimensional things, right, that have simply length. So one dimension means we can put a 1 up here for the exponent. Area is a two-dimensional thing, right? It has both width and depth. In this case, so then we can put a 2 here, so it's for its two-dimensionalness. So we not only multiply it horizontally, but also vertically. Again, I'll do a quick example. If I have a square right here, and I want to make it 3 times wider and 3 times taller, right? It's going to be something like this. And it's pretty clear that since it's 3 times wider and 3 times taller, it's 9 times greater area. Okay? A lot of people are going to think, oh, 3 times wider, 3 times taller, 3 times area. No, that's 3 times the perimeter, but 9 times the area. So whatever the scale factor is, you need to square it when you're talking about the area of a proportional change, where we change the x's and y's the same. Okay. We talked about both these, but essentially there's 4 scenarios here. One is where you don't have a proportional change, where we just change the x or just change the y. In that case, we take our scale factor and then use that to find the area. Just multiply it across. When it comes to the perimeter in those, there is no constant rule. So again, we don't have a pattern or anything we can rely on. The other type of change is where we have a proportional change, where there's the scale factor is being used both horizontally and vertically in the same amount. In that case, if we take our scale factor, the new perimeter is simply the original times the scale factor. So just like we did area before, and now since we're going in 2 dimensions, the area is changed by that scale factor squared. Okay, so you have to keep track of those four things. Okay, we'll do an example here. Again, this is non-proportional dimensions. It asks us to find the area of the figure. You didn't see that. We'll figure it out later. The area of this figure is, again, just base times height. So in this case, 6 times 5 gives us 30. What I want you to start doing is when it asks for the transform figure, instead of plugging it into this formula that they have, I want us to just skip ahead to the end. That's the power of this ability, right? So the original area is 30 feet, and then the transformation, it says, multiply the length by 2. So it's going to be 2 times wider, right? So draw like a little example here. It barely fits. Okay, that's fine. Something like that, right? So it's going to be 12, and then you can do 12 times. No, we don't want to do all the math. But all we need to do is realize since it's 2 times greater in length, the transform figure will have twice the area. Twice 30 is 60. So that's where we can just skip straight to the 60. Let's try this one. We got the area of this trapezoid, and then let's just figure out the area first. So trapezoid, the pattern is we take the average of the 2 bases, so in this case 12 and 3, so 12 plus 3 divided by 2, and then we're going to multiply that thing by 8. So 12 plus 3, well, that's 15, divided by 2 is 7.5, times 8, well, times 2 brings us back to 15, and then we just have to do 4 15s, so that's 15 plus 15 plus 15 plus 15, or 60. So we can come up with 64 for the area of this trapezoid. And then it says multiply the height by 0.5. So essentially half the height. What happens to the area? Well, it's going to be half the area, right? Because in one dimension, we're halving it. The scale factor is 1/2, so therefore we multiply that scale factor of 1/2 by the area, gives us 30. What we don't want to do is work through this whole problem all over again, right? You've already calculated area. It's easy enough to mess up on something like this. So let's just skip straight from the 60 and go down to the 30. We don't actually have to do all these calculations that are right here. We can just skip it straight ahead to the 30. They're trying to get you to realize that that scale factor is 1/2, so the area changes by 1/2. Again, only works because we're going in one dimension. Okay, see if you can do this one. I've half solved it for you. So it says find the area of a triangle with vertices, blah, blah, blah. Then apply the transformation and determine the new area. So I went ahead and gave you the area of the original. So the area of the original is 36. Here is the transformation right here. See if you can figure it out. I'll go and pause. Okay. Since the scale factor is 4, hopefully all you did was multiply this value by 4. When you do, you get 144. Please don't regraph that whole triangle. It's a ton of work. It's much easier to just go 36 times 4 equals 144. Similarly, we can do the same thing. We're doing the proportional changes now. In this case, we have a circle. We want to find the circumference and area of the circle. Okay, we can do that. That's 2 pi r and pi r squared, right? So the circumference is 2 pi r. 2 times 4 times pi is 8 pi. Pi r squared, pi times 16 or 16 pi. Okay, so we have the area and the circumference of the original. And then the transformation is multiply the radius by 3. So the scale factor is 3, and this is a proportional change. So it's going to change the diameter going this way by 3, and it's going to change the diameter this way by 3. So the width and the height, they're both being multiplied by 3. So the transformed figure, its new circumference, we could calculate it, but we might as well just jump straight there. The original had 8 pi. The new circumference is going to be 24 pi, right? We're going to multiply by that scale factor of 3 in order to get 24. Okay, this is the one people mess up on a lot. The original area is 16 pi. What is the new area for the new transformed circle? A lot of people put 3. It is not 3. Remember, we're working in 2 dimensions, and both of those dimensions have a scale factor of 3. So we go 3 this way, 3 this way. That's a grand total of 9. So we multiply that 16 by 9, and that gives us 144. Hooray, which is 3 squared. Okay, 2 more here. For this one, I'm going to go ahead and cheat a little bit and give you the original figure data in a second. But just a reminder that this is an isosceles right triangle, so that's 6 and 6, so therefore this is 6 square root 2 for this length, and it's a square. So the perimeter is 24 square root 2, right? 6 plus 6 plus 6 plus 6. And the area is 6 times the square root of 2 squared, 36 times 2, or 72. Or you could use their formula, sure. The transformation, let's see, it says multiply the length and height by 1/3. So we're shrinking it, into 1/3 the original size, both width and height. So therefore, what should the new perimeter be? And what should the new area be? Again, I'll give you a second to kind of figure this one out on your own. Pause. Okay. Hopefully, you came up with 8 square root 2, because that's 1/3 of 24. And hopefully you came up with 8 for the area, because that is 1/9 of 72. Why 1/9? Well, we had 1/3, and then we squared it. So 1/3 squared is 1/9, right? Oops, went that way. Okay, so just a real quick summary. When we're doing proportional changes, if our scale factor is A, right, here's A, our scale factor, the perimeter changes by a factor of A. A, right there. Changes by a scale factor of A. Another way to write A, you might say, is A to the first power, right? You guys, A to the first is the same thing as A. Area changes not by A, but by A squared, right? Area is a two-dimensional thing. Perimeter is one dimension, right? Length. Area is length and height, or width and height, something like that. And then volume, just want you to think out loud here. Volume will change by what? Well, volume is a three-dimensional thing, so therefore it's going to change by A cubed. For those of you who figured that out, gold star. Cool. I don't think there's a lot of questions on this, but just be aware. Okay. This one says, find the circumference and area of the circle. Then multiply the radius by 0.25 or 1/4 to determine the new circumference and area. I'm going to walk you through the circumference, so then this should be super short. The radius is 12, therefore the circumference is equal to 2 times pi times r, which is 12, or the circumference equals 24 pi. The area is pi r squared. R is 12, so it's 144 times pi. Okay, see if you can figure out the new circumference area from that. I'll go ahead and do another pause. Okay, hopefully you got these values. The original was, we get 24 pi and 144 pi, right? The new circumference is 6 pi. Why 6 pi? Because it's 1/4 of 24, right? That's the scale factor, is 1/4. The new area isn't 1/4 of the old area. It should be 1/16, right? The old area was 144. So the new area is 1/16 or 9 pi. Again, you should be able to just do these jumps without having to do all the calculations of everything in between. Okay, good luck. We ran pretty late, so have a good one.